Alrighty, we are on to parallel circuits. This is example 7. We know that when we have, well, first of all, take time to draw this circuit and also show the direction of conventional currents. Remember, we have several junctions right here. So over here on the left, I'm going to start with, say, like fat line showing all the current going this way. And then that current splits into smaller right here, and it goes through this resistor. Then a little bit thinner line keeps going through this one. And then at the next junction, it's going to also split, and whatever is left over is going this way, and then through that resistor. So ultimately, all of these are different currents. The only thing in resistors that is the same, in this case, in a parallel circuit, is the voltage. And remember, it didn't work for us in the real lab because our resistances were not zero for wires. So wires actually were using a little bit of energy. But if we pretend that wires are ideal, non-existent, and non-resistive, then our total our total voltage in the battery is the same that every single resistor gets. So again, since we're pretending this is an ideal parallel circuit, no energy is lost on the connection, meaning all those wires, and I can just say that this guy has 12 volts, that guy gets 12 volts, and the last resistance doesn't lose anything and gets 12 volts again. So total current, I could figure out resistance first and then go for total current. Perfect. Or I can get separate currents, and that is what I'm going to do because that's simply easier. 12 over 2. The current in this resistor is 6 amps. Boom. Then I got again 12, but now over 4. That's going to be 3 amps. Which should make sense. The one that has double the ohmage or double the resistance will get only half the current. And then finally, 12 divided by 6, oops, not 16, 12 divided by 6, that will be only 2 amps. 3 times the resistance, 1/3 of the current. Boom. So then I total, I can find as 6 amps plus 3 amps plus 2 amps. That's going to be 11 amps. Now, we have found current. We didn't really calculate potential resistance or potential difference across, not potential resistance. What did I just say? So, we calculated the current. We knew that potential difference across each resistor was 12 because they're connected in parallel. Calculated total current by adding individual currents and got our 11 total. Find equivalent resistance. Well, I know that V total, no matter what kind of what kind of circuit we are dealing with, over I total should be our equivalent. So in our case, it's 12 volts over 11 amps. And that will be calculator. A little bit over 1.9-ish or something like that. 12 divided by 11, 109. So 1.09. And that's going to be ohms because we're finding resistance. Now, it says find equivalent resistance 2 different ways. Using Ohm's law, check, we just did. and the rule for resistance in a parallel circuit. That is the reciprocal of a reciprocal. So I know that if we have a parallel circuit, then we're going to do this. R1 plus 1 over R2 plus 1 over R3. So in my case, it's 1 over RE will be 1 over 2 plus 1 over 4 plus 1 over 6. So you can use your calculator and get those 1 over 2 plus 1 over 4 plus 1 over 6. What I'm going to do, I'm going to get the common denominator of 12, and then to get 2 to 12, that's a 6, plus to get 4 to 12, that's a 3, and then to get 6 to 12, that's a 2. So that's how I get my 11 over 12, but be careful, that is 1 over R equivalent. Then R equivalent is the reciprocal of the reciprocals, and it's going to be 12 over 11, which again is 109 ohms. So that's how you find it. A second way using the rule for resistances in a parallel circuit. Again, please, please, please watch this follow through. Do not just copy the screen, because that's not going to help you in the second, in the 8th actually. Example number 8. Kind of give you a lot of room for you to fill this in. All right, so on to example 8, or rewatch example 7 if you didn't get it the first time. Thank you.